There are any functions, and G can be open loop system, can be closed loop system, any functions. Okay, and again, here in the frequency domain analysis, we work on is replace S by J omega. Then we want to plot the Nyquist plot is made by this. So, for example, here we have a G J omega. We can calculate its magnitude, and also we can calculate its the angle. Okay, and for example, here we can repeat calculation of this one for omega equal to omega 1, omega 2, omega 3, etc. As many as you like. So we can calculate the magnitude for corresponding each of those things. So once we have those things placed, then basically the Nyquist plot is to plot on the complex plane. Okay, so let me make up certain numbers here. So for example, here we calculate this will be the magnitude. For example, this is a magnitude. Let me make up one, okay? So for example, if this would be say 1, this is the 0 degrees, and this is the 1.5, and this is the minus 45 degrees, and this is say 2, and this is minus 90 degrees. No, let me make up one. Okay, 2 minus 60 degrees. Okay. So once you have those things, you simply label its magnitude on its point on the complex plane. For the first point, its magnitude equal to 1 and 0. So the first point corresponding to here. So this point is the location, is the representation of the G J omega on the complex plane. So here I would say this is the part of the G J omega. This is a complex plane for G J omega. Again, G is a function. G is an arbitrary function. When we introduce the argument with the complex numbers, basically we are dealing with this one is we call the complex functions. Okay, so basically that is the definition of function algebra. Right now we're dealing with, in mathematics, this is the complex functions. A complex function will always be represented in a complex plane. Okay, so this is in the imaginary part of the Gj omega. Okay, so right now for this one we try to label. So this point is a magnitude equal to 1. Okay, so let me put a scale. So for example, this is 1, 2, minus 1, 2, 1, 2. Okay, 1, 2. Yeah. Okay. How about this? We just work on the grid. Okay, and here I'm drawing. Each unit have the units. This is the unit scale here. Okay. So now for this one, we have this one is here. So that is a 1. Corresponding is this one. The second point is 1.5 and minus 45 degrees. Okay, taking 1.5 is about here, and minus 45 degrees, so that is here. Right. So right now I'm plotting the point on the complex plane. If you remember before, if this is a complex plane, 1 plus 1j, and that is here, and 2 minus 2j, and 2 minus 2, so that is 1, 2, 1, 2, that is here. You know what I'm saying, right? Okay. So now for the third one, that magnitude is 2 minus 60. So let me, this is 2 and 60, so I would say that is about here. Okay. So if you keep doing the things, then you can trace the point you plot, you calculate it. somehow something arbitrary. Okay, so this one basically constitutes a portion of the body plot. Sorry, the Nyquist plot. You always keep doing things until omega is from 0 to infinity. Where that starts, where it ends, that constitutes a half portion of the Nyquist plot. The other half is from -0 to -infinity. That constitutes the whole things. You good? Okay. So this one basically, again, this one drawing, I show a few features. The Nyquist plot of a certain function basically is on the complex plane of that functions. You simply is calculate magnitude, phase, angle, and then you place the points on the complex plane. That's it. So that is the first exercise you're going to learn. And then the second one is as a good exercise, we like to label the corresponding frequencies onto the curve. For example, this point corresponding is omega 1 would be used to calculate. This point corresponding is omega 2. This point is omega 3, etc. And for example, sometimes we say, okay, following the trending of this curve, that is corresponding to omega to infinity. And then from this point of somewhere, maybe say here that is corresponding to omega equal to 0. People like to keep a good exercise by noting where point start, what that means corresponding to omega equal to 0, where it ends, corresponding to omega go to infinity. So here kind of the good exercise, try to label and then help you and help people. Okay, good? Easy, right? Okay, so that's basically the definition for the Nyquist plot. And so here I want to show you again the Nyquist plot of a few generic functions. In this way, we can use those kind of generic functions to help plot the more complicated functions. So here, for example, the Nyquist, we can have a section.